can't think of any more human activity than conducting science experiments.
The game I play is a very interesting one. It's imagination in a tight straitjacket.
The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together.
What I always think should be the basis of education is not answers, but questions. We should teach kids how to question.
This is BLab Codes. My name is Hamid. In this abridged episode, we talk to Sandy about his research project, which aims to build nanocages in hopes of trapping carbon. To hear the full version, go to blabcodes.com and subscribe to our podcast.
So at the moment we're working on really porous nanomaterials and the discrete porous nanomaterials. So instead of things that polymerize into a larger, into a big framework or a polymer.
Right. And a polymer is just a long chain of something, or
repeated
units.
Connected.
It's like a different Lego pieces, the same Lego pieces, just connecting over and over and making long chains of whatever.
Exactly.
Yeah.
But imagine if then you built those Lego pieces into really big, porous structures, which means a lot of area on the inside, a lot of surface area. If you built them into bigger, discrete ones, units, and then put them together. And now what this does is this increases the surface area on inside of these materials by vast amounts. There's part of what I work on are called molecular cages. As I was saying, we use these metals to build these organic molecules into these pretty much big hollow balls. And the idea is that when you have this insane amount of surface area, and I'm talking as in 1 gram of this stuff can have, if you could unfold all these little nano balls, almost 1 gram would have enough surface area to cover a football field.
Wow.
Easily. And so, and that's an old stat, there's been bigger ones produced since then. But the cool thing about when you have porosity in nanomaterials is it allows you to do lots of really cool things. And that's like the gas trapping was one. Catalysis. So if you imagine things in solution, whenever things react in a solution, there's billions and billions of solvent molecules per your target molecule, right?
Like solvent molecules like water, for instance.
Exactly. You've got salt dissolved in water. And for these things to react, they've got to travel through all this solvent that they're interacting with and then collide with enough energy to produce the product. But if you can, the chances of them doing that, statistically, when you think about it, actually really low. That's why you've got to leave reactions on for a week or, but if you could use this big cage and the solvent and say just 2 of your reagents come in and can bounce around inside this cage and react, the chances of them colliding and producing this reaction gets increased dramatically. So you get catalysis. You speed up the reactions, or even have sites inside these pores that actually increase the rate of the reaction by, say, mimicking biological molecules and things by having these open metal sites and things that can produce fast reactions. You've got drug delivery is another avenue. Housing a molecule and getting it somewhere. There's so many uses. Something that my thesis is focusing heavily on is what's called spin crossover, and it's getting into the physics that we described before. So it's where you're taking a metal ion that has no unpaired electrons. When something has no unpaired electrons, it's not magnetic. We call that diamagnetic. But then,
so normally these metals would have paired electrons.
Depends. It depends on the metal. But the important thing about this property is that this spin crossover is that you take a metal that either has no unpaired electrons, it's not magnetic, and either with temperature, pressure, or light, you can make it transfer to one that does. Permanently until you reverse that.
Oh wow! So you could.
So you go from not magnetic to magnetic.
Dude, that's magical. So you could essentially take a metal that's not magnetic at all and turn it into a magnetic metal.
Yeah, and the and you can do it in heaps of different ways. And the applications of this are in sensors, and the big one is in data storage. Because if you think magnetic and not magnetic,
That's 0 and 1.
0, 1, but then there's ones where they don't just go magnetic to non-magnetic. They go through steps where they might go from, if you have, say, instead of, as I was talking about these discrete molecules, if it has one metal, then it might do that. It might go from just, say, on to off, 1 to 0, magnetic to not magnetic. But if in one discrete molecule you've got 2 or 3 metal centers that all do the same thing, but at slightly different temperatures, then you're not just dealing with ones and zeros, you're dealing with 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, you know.
Right.
So the code that you can encompass becomes, so this is quantum computing and data storage, quantum data storage.
Wow, that's interesting. Just in terms of turning a metal into a magnetic one. So let's just say it's a metal that doesn't have any magnetism. So that's when you have 2 electrons that are paired, and if you take away one of those electrons, then what? So how do you make it magnetic? Is the question I'm asking.
I guess a key thing to understand first is there's a difference between the magnetism that we usually comprehend, which is say we take a magnet and stick it.
With iron filings.
Yeah, with iron filings, and they attach. That's magnetism on a bulk scale, which means that the metal ions that have these, as I said, unpaired electrons within the material, their magnetic moments all align perfectly, so that when you bring a field near it, it can be attracted. There are some bulk solids like that where the individual metal atoms are magnetic, but because they're all aligned in opposite directions,
they cancel each other out.
So this is different. This is magnetism for a single discrete molecule, right?
Okay.
And that builds up in the solid when it in the crystal lattice. And as an answer to your question, how
do you make them magnetic?
Okay, so for anyone studying chemistry in the HSC, electrons can exist in energy states. They're called orbitals, molecular orbitals, and a cool little law in physics. You can only have 2 electrons in one molecular orbital, and they're paired. Electrons have this property. It's called spin. Pretty much, it's kind of just like the orientation of their magnetic moment, right? So if you imagine 2 electrons have this negative electronic moment that's orientated in a specific direction. If you put them in the same energy state, this orbital, with that same orientation of this negative charge, this negative, it's not going to be they're going to be opposing, right?
Right.
And so to fit 2 in an orbital, one is flipped with the orientation the other way around.
Right.
So only 2 can fit in an orbital. So if you imagine, now if you have a metal with uneven number of electrons, that will automatically have a spare electron.
Yeah.
Right? But, so we can take metals that have 6, an even number, and we produce organic molecules that coordinate, as you were saying, with them, so bind to the metal centers. And they have just the right energy of interaction to, when you increase the temperature or pressure or light, it allows 2, instead of saying if I've got these 2 that are paired in the one orbital, it allows it to go, which is at that stage the most energy, the lowest energy state.
So stable.
The most stable state.
Yep.
It actually allows, as you increase the temperature, this state where one of those electrons moves up into a higher energy orbital to be the more stable state at that temperature. So you're not taking away electrons or adding electrons, you're just moving the energy state that it's within, and then by doing that, you're changing the magnetic properties of the material.
Okay, let me just see if I understand this correctly. So electrons exist in orbits, and for those who don't have a chemistry background, you can think of an orbit like the sun, and you have electrons like the obviously this is very simplified because we know it's not like this. There's different shapes, s orbitals, but let's be whatever. But we'll just go with a simple analogy. You have the sun and you have these planets orbiting them. So Mercury and Venus are the inner orbits, whereas like Neptune and Pluto would be the outer orbits. So if you're in the outer orbits, you have more energy, and in the inner orbits you have less energy, right? Would that be correct? So as your energy state increases, you jump to a higher orbit, so you jump to an outer orbit.
Yeah.
So, and you're saying that you could have these two electrons existing in the same orbit only if they have opposite spins. So it's almost like being in a conservative country where you can only get together if you're the opposite sex.
Exactly.
As soon as you're showing any sort of affinity, like there's no way homosexuality is going to be tolerated in certain parts of the world. So you can only accept opposites, right? Opposites attract.
Except to make them fit, you wouldn't put them in the same room and just turn them upside down. Which is what they're doing with the electrons.
Yeah. That's so funny. And so as long as those opposite electrons are together, there's no magnetism. But as soon as you kick one out, for whatever reason, increasing the temperature, the energy, that one electron jumps to an outer orbit. So it might jump from the Mercury orbital to the Earth orbital. And over there, it's by itself. And that's what causes the magnetism.
And now you've got two by themselves.
Oh.
So, so you got two, you go from none to two.
Right.
And so, the example, the systems we use, we go from none to 5 amperes. So it's quite interesting, and you can play with these different metals. So there's a couple that specifically are better than others because the energy levels of those orbitals are within the region that we need. That's
so interesting. So does that mean that electrons by default are electromagnetic? They have a magnetism to themselves.
Oh yeah, they're a charged particle, right? So any charged particle has its own
magnetic
moment. Protons the same. They have a magnetic moment because when you think about it, what gives off an electric charge, electric field, a magnetic field, is a point of electric charge that's moving, right? Like when you're in year 12, when you took that magnet through a coil, and you create your own little generator. Right. But the same thing with an electron. They're constantly buzzing around, right? A better way to think of it, rather than the orbits, is just a big smear of electrons just around,
like a cloud.
Because technically, they exist everywhere within their orbit at once. So it's whenever you get a charged particle, it's moving. It's producing a magnetic field. Right. And so they do, and we use that in a lot of chemistry and physics. We actually use that to our advantage. The fact that if you've ever done NMR or anything like that,
right. Yep, I've done a bit. I remember from undergrad where you're looking at the peaks to determine the structure of the molecules.
And so what you're actually looking at there is they're probing the magnetic moment, the spin state of the nucleus, right? But they know of the protons and the neutrons, but they know that signal that they get from that is altered by the magnetic field that the electrons are giving off around each proton or neutron, you know what I mean? So they can distinguish the environment of different atoms by
looking at the magnetic moment of the nucleus of the atom.
And how that's affected by the electrons.
Right. That's interesting. Your analogy of, getting a battery and essentially getting a long piece of wire and wrapping it around a nail and then just, attaching that to a battery. That's just electrons moving from the anode to the cathode, correct?
Yeah. Well,
and that creates magnetism because you could essentially make that...
A moving charge.
Yeah.
The electrons are moving within the material, and that produces an electric field.
Dude, you've just blown my mind. Now I know why magnetism works. Oh shit. Awesome. This has been a really interesting conversation for me. Check out our podcast on blabcoats.com. Subscribe on iTunes, Stitcher, or wherever you find your podcast by looking up BLab Coats.